Let's now think about how we can solve the zigzag problem. The default solution many people consider is the so-called brute force solution. With most problems you see, you'll be able to immediately think of the naive or the brute force solution. And I'm sure you've already thought of it. And it is, let's just generate all subsequences and then check if each subsequence is zigzag. Of the subsequences that are zigzag, just pick the longest one. And that sounds simple enough, so let's write it down in the ideas box as our first idea. So generate all subsequences for each generated subsequence, check if it's zigzag, and then finally of all zigzag subsequences, pick the longest one, right? So once the idea is out there, your immediate next thought should be about its time and memory complexity. We'll cover the ins and outs of complexities in the next section, so for now I'll just fill them in. So the time complexity of this idea is going to be n times 2 to the power of n, and the memory complexity is going to be on. In the next section you'll learn how to compute these yourself, don't worry. So would that approach be practical given the problem's constraints? Well, the input sequences can get quite long, as we saw in the constraint section. At 50 numbers, we'll need to generate 2 to the power of 50 subsequences. And this is a pretty huge number and would take hours or days to compute. So we need a more efficient solution. But how can we come up with it? Well, one of the approaches for idea generation is to simplify the problem. So how can we simplify zigzag? Well, zigzag requires us to find a subsequence that goes up and down. What if we were just trying to find the longest subsequence that only goes up, or what's known as the longest increasing subsequence? And this is a pretty standard dynamic programming problem, right? If you've looked at our algorithm section, you should already be pretty familiar with it. The way you solve this problem is by trying to extend the longest subsequences ending at each of the previous elements of the sequence. So something like, up 0 equals 1, and then up I equals the maximum of up j plus 1 for each j smaller than I such that aj smaller than ai, right? So look at all the previous elements, look at all the subsequences ending there, and if ai is greater than aj, try to extend it and just pick the best of those. And similarly, we can define down I, right? Down 0 equals 1, down I to be the length of the longest decreasing subsequence ending at ai. So this is great. We broke down the problem into two simpler problems that we know how to solve. Now, how do we solve zigzag? Well, all we need to do is slightly tweak the definitions of increasing and decreasing. Concretely, if up I, this, right, is the length of the longest zigzag subsequence ending at ai, which ends with an increasing segment, and down I is the length of the longest zigzag subsequence ending at ai, which ends with a decreasing segment, then we can say that up I equals the maximum of down j plus 1 for all j smaller than I such that ai greater than aj. Let's just fix this. And then down I is going to be the maximum of up j plus 1 again for all j smaller than I such that ai I smaller than aj. So basically we just try to zig and zag. That's why up I uses down j and down I uses up j. And the solution of the problem would be the maximum of any up I or down I from 0 to n minus 1. Feel free to pause the video at this point if you're not sure about what we wrote down and take a look. Now let's clean this up and write it in the ideas section. We should say something like up I is gonna be the length of longest zigzag subsequence ending at ai and going up, and then down I is the length of the longest zigzag subsequence ending at ai and going down. And then we can say, let's just get a little bit more space, and then we can say that initially up 0 and down 0 are going to be 1s, and then we're going to keep those, and then the solution, we can say initial, right, and the solution is going to be the maximum of up I, down I for 0, I, n, right? So this is a pretty succinct description of our idea, of our dynamic programming idea. We defined up and down, we set some initial values, we then wrote the logic for the other cases, and then this is how we come up with a solution. Now that we've written it down, it's now critical to turn to the time and memory complexity of this solution. In the next section, we'll talk about how you compute it, but for now, let's just fill those in. So the time complexity is going to be n squared, and the memory complexity is going to be linear again. Now, that looks like a solution that's a lot better, right? Not only is it better, but at n equals 50, it's going to be very, very fast. So it's a great solution that we can now go ahead and implement. One final note before we do this. We could have come up with the exact same idea by applying another approach to idea generation. And that's the thinking about similar problems approach. What problem is zigzag similar to? We're trying to come up with the longest subsequence that matches some criteria. Well, that sounds a lot like finding the longest increasing subsequence, right? And from there, you can think about how extending the well-known dynamic programming solution to the longest increasing subsequence can help with solving zigzag. So that's it for idea generation. Now let's look at how we came up with those complexities.